Welcome to A-Level Physics. It is time to look at how the world generates its power. In your last unit, you discovered that moving charges create magnetic fields. Now we explore the profound reverse of that rule. Changing magnetic fields can induce an electromotive force, which in turn drives an electric current. This single physical principle is the foundation of the modern electrical grid, explaining how mechanical energy is converted into electrical energy in power stations worldwide. This unit transitions your understanding from static magnetic fields to dynamic ones. Let's look at the sequence of topics you will master, starting with magnetic flux. Before we can calculate an induced voltage, we must quantify exactly how much magnetic field passes through a given area. We call this magnetic flux. It depends on the magnetic flux density, the area of your coil, and crucially, the angle between the magnetic field and the normal to that area. Getting this geometry right is your first major hurdle, but it is the essential foundation for everything that follows. Once you can calculate flux, you are ready to determine the size of the induced voltage using Faraday's law. Faraday's law states the induced EMF is directly proportional to the rate of change of magnetic flux linkage. A hallmark of Cambridge Paper 4 is translating between graphs. If your magnetic flux oscillates as a sine wave, the gradient gives you the rate of change. The induced EMF is driven by this gradient, mapping out a negative cosine wave. The steeper the flux graph, the higher your induced voltage. An A-star candidate always links the peaks of the EMF graph to the steepest gradients of the flux graph.
Next, we tackle the direction of that voltage with Lenz's law. If Faraday's law gives you the magnitude, Lenz's law gives you the direction. It states that an induced electromotive force always acts in a direction to oppose the change that created it. This is not just a rule for finding the direction of a current, it is a direct consequence of the conservation of energy. You cannot get electrical energy for nothing. You must do mechanical work against an opposing force, otherwise you would create infinite energy and violate fundamental physics.
Finally, we apply these laws to real devices in the induced EMF topic. Here we apply fundamental laws to practical engineering. You will calculate the motional EMF generated when a single straight wire cuts through a uniform magnetic field. Then we scale up to alternating current generators, where a coil rotates continuously in a magnetic field to produce a sinusoidal voltage. This is where abstract physics meets real-world power generation, and it is frequently tested as a dedicated 12-mark question. By the end of this unit, you will be able to calculate magnetic flux, apply Faraday's and Lenz's laws to find the size and direction of an induced EMF, analyze gradient graphs, and model real alternating current generators. You are now ready to start Topic 1 and define magnetic flux.